Right, we are going to be covering generating functions, which are an application of algebra in combinatorics, as we will see. So firstly, what we want to think about is if we look at the expansion of 1 plus x to the 5, and you take some generic coefficient like x squared, what is the coefficient of x squared? Nag?
1.
Are you sure? So in this expansion, what is the coefficient of x
Oh, sorry,
squared?
5 choose 2.
Why? That's
Why?
the question.
Because when you expand the brackets, it's
Yeah.
basically figuring out the number of ways we can try and get an x squared coefficient from
Exactly.
multiplying.
So if you write out all the brackets, you have 5 binary choices between adding nothing to the exponent or adding 1. So to get 2 in the exponent, you have to choose the right one 2 times. So 5 choose 2. And this is basically how we can apply it to combinatorics, because when we count stuff, we're going to attach it to the exponent. Then the coefficient is basically how many ways we can sum to that exponent. We are going to see in a second. So this is the formal definition. It's basically just taking a sequence and just putting it onto coefficients of a power series. And in maths today, we basically talked about it. It's like an infinite polynomial. And this, like, it's infinite. Just remember that. So if we're plugging values in later, they will have to be less than 1. And you can have any sequence in that you're plugging in. So it could be like 1, 0, 0, 0. So then it'd just be 1. Or 1, 1, 1, 1, 1, and then a bunch of like zeros would be like 1 plus x squared plus x cubed, and then nothing else. And it could even be like the Fibonacci sequence. And you can actually, hey, what have I actually done? Okay, you can use generating functions to find a closed form expression for like the nth term in the Fibonacci sequence, which we could do today if you guys want. But so, oh no, not this yet. So can we think, if we're rolling a dice and we're finding the sum of rolling just one dice, can we think of what the generating function might be? So if we do it, we can add 1, 2, 3, 4, 5, or 6 to our exponent, right? So it's going to be x plus x squared plus x to the 6, right? Just for one dice. So what if we rolled 2 dice and we took the sum of that? Well, we need to add it one time, then we need to add it to the exponent a second time, right? When we're adding exponents, we're multiplying terms. So we take this all and square it, right? And then this is where geometric sums will come in. Because say we're adding up just some like integers, right? Non-negative integers. And we can add, if it's non-negative, we include 0, by the way. So we can add nothing. We could have our non-negative integer be 1, 2, so on. And you might recognize this is a geometric sum with a common ratio of x. And if you write the sum to infinity, which is like the power series, right, you will get 1 over 1 minus x, I believe. So that will help you simplify the generating function. And then what we do is we want to find a coefficient because it will tell us something in the sequence. And we can use this to help us. So we have some choices now. What we could do is we have this first problem. It's just like a basic counting problem. Or we can do this problem from BMO2 of 2019, which is a bit more advanced. Or we could look at finding like a general form for Fibonacci numbers, but that might go wrong. So what do we want to do? The main question. Okay, the GIF, like, so if you ever was walking into the BMO2 exam hall before doing this, and I just read this question, like this is how I'd feel reading the question pretty much. Like, because this is quite an intimidating question. Oh my. So, can anyone think off the bat of what a generating function might be for summing elements from 1 to p minus 1, and you can only choose one at most, yeah?
Would it be x to the 1 up to x to the 1?
So how are you writing that? Like
X plus x squared plus x cubed.
x squared.
X to the p minus 2, x to the p minus 1.
So this is nearly right, but here in our exponent, it's like, what is the coefficients, right? Because we have coefficients, and the exponent is this is 2, represents a sum of 2. So this is how many ways we can sum to 2, right? So we want to find, so this is like when we write it out, it will look like this. So maybe the question's a bit bad, I'll just move on. So if we go through each element in 1, 2, 3, all the way to p minus 1, we can either add it or not add it, right? So this should remind you of 1 plus x to the 5. Instead of all of them adding just 1 or 0, you can add 0 or the number here, right? So it'd be like 1 plus x, 1 plus then x squared instead of x, right? All the way up to p minus 1. So we have the curve, like if you write it out, it will look like this, right? And we now have a form with a bunch of brackets. If you want to figure out how to find the coefficients which are divisible by p, because they represent how many like subsets have a sum divisible by p, if that makes sense. Yeah, so this is the generating function, and then this is how we get a total number of subsets, which like help you think. Okay, you might think that they're distributed evenly, right? You might think 1 in every p subsets will have a sum divisible by p. You might be able to guess, oh, this might be around 2 to the p minus 1 over p. So if we take an easier example, because this is quite intimidating, if we just wanted to get the even coefficients, right? We want, so every other, we want this to go to something, this to go to 0, or something, this to go to 0. And in this example, we evaluate the brackets at 1 and minus 1. Well, not the brackets, but like you look at this sum when you're trying to find coefficients. So you see when you plug in 1, all of the x's go to 1. Plug in minus 1, they alternate between 1 and minus 1, right? Like they're rotating from 1 to minus 1, the period of 2. Then when you add them up, you will only get the even ones. And you've counted them twice, by the way, so you divide by 2 in the end. So now we need to think, we need to plug in some values into f, but instead of just getting the even coefficients, we want the ones divisible by p, right? So any ideas how we could do this? Yeah.
We substitute p and negative p.
P and negative p. That would set, this would be p to the 0, p to the 1, p squared, and then minus p would be like, what's it, minus p, or minus 1, like whatever. So if you add them up, you want like c underscore p, like, and 2p. Only those ones should have values, everything else should be 0, right? So it will be in the next slide, but what we want is, if we look at adding 2 of them, f of a plus b, and we look at, so if we write f of a as a times c0 plus a to the 1 times c1 plus a squared times c2, and f of b as b to the 0, c0, so on. And then you're going to add them like in columns, and you're going to look at the coefficient like the variable, and the variable like the coefficient. You'll get a plus b, c1, and so on, right? So we want some numbers where the sum is 0 if you're raising them to any power but p, pretty much. And so you guys know like Vieta's like roots of polynomial, right? So if you take p, so p, do you guys know about like roots of unity? Yeah, kind of. So it's basically solutions to this equation, x to the p equals 1, right? Then if you look at the like Vieta's formula, right? The sum of all the roots is minus b over a, right? What is b in this question? It's just 0. So here, all of these will go to 0. And the reason why if you raise it to the p, it won't go to 0 is because, like, if you raise them to the p, you get 1, which is from the original equation, right? So what we now need to prove is that it will also work for like raising them to the squared and the cubed, and not just like for this one. So what we do is we write out, what's it, like Euler's formula or something, yeah, for complex numbers. And when you write it out, then you raise it to a power, you're multiplying the argument. So if you imagine like a circle, right? And this is, the circle is a radius of 1. So all of the square roots of 1 will lie on the circle, right? And like all of the angles, like they're all equal, like because you're rotating some fixed amount around the circle. So when you multiply the argument, so what is this first angle here? It's like, if you take p equals 5, it should be 2 pi over 5, right? And that's how you rotate between each one. So if you multiply it by 2, you're going to rotate it once, and you're going to rotate it twice around the circle, right? You're going to get the second root of unity, right? And then if you rotate it more than two, like if you rotate it 7 times, right? This might remind you of modular arithmetic because you have numbers in a circle. You 1, 2, 3, 4, 5, and then 7. So you'll notice it's the same as rotating it 2 times, right? Because when you multiply it by 5, you're just doing a 2 pi rotation, which is the same. You just end up in the same spot. So that is where the justification that if you raise a root of unity to a power, you'll just get a different root of unity. And that will be given by, where have I written it? Yeah, this will be given by like the current root of unity multiplied by the power. So taking the second root to the third power, you do 2 times 3 equals 6. And then you have to take a mod p, because we've just looked at the circle, and you will take it to that root of unity. Then finally, we're going to show that if you take all of them to the squared, all of them cubed, so on and so on, if you notice, if you're familiar with like residues, mod something, it's basically all possible remainders. And since all of the powers, right, the power is constant, and you're having z0, like zeta, it should be zeta, but it's 1 all the way to p minus 1, right? So when you multiply, so we're trying to find 1 plus zeta 1, this whole product, right? So to do this, we go back to z to the p minus 1, and we use the fact that these are all the solutions, right? Minus 1. And if you have the solutions to a polynomial, you can factor it, right? As z minus, like, zeta 0, z minus zeta 1, and so on and so on. And then to get 1 plus zeta 1, 1 plus zeta 2, we're going to put in z equals minus 1, right? And then p is an odd number, so there's an odd number of brackets, right? So I'll call our product big P. We'll get minus 1 to an odd power, so minus 1 equals. So since these are all minus 1 minus z0, z1, so on, if you take the negative out the bracket, right, it will be 1 plus zeta 0, zeta 1. And there are odd number of minus signs to take out. So it'll be minus. But we have to remember z0 is like the exception here, it's just 1. It'll be minus 1, which is minus or plus 2, and p. So 2 times p, or whatever, minus 2p equals minus 2, p equals 1, right? And then this product will unpause the board now. This product, remember, you have to calculate it p minus 1 times, we already found one of them, and it's equal to 1. So the coefficients, when we times them all, when we add them up, so p roots of unity, we add them up, we get 2 to the p minus 1 plus p minus 1. And we remember, when we add them up, let's go back. Okay, my laptop is working this time, but when we add them up, we're counting them p times, right? It's p times all the coefficients divisible by p, everything else is 0. So just divide this by p, and if you want to like check your answer, like, is this an integer? I'm sure some of us know a theorem that can help us, made by a guy called Fermat.
Fermat's digital theorem.
Yeah. So is this an integer?
Yes. Yes.
Yeah. Okay. And that is the answer.
And we are done.
Yeah. QED. And we are done. QED. Shall I pause the board right there? Oh no, we already have the proof.
Oh yeah.